We'll create a snake game and an Electron cloud simulation to compare Claude 3.5, GPT-4o, and GitHub Copilot. Since Claude 3.5 has been released 3 weeks ago, there have been videos after videos about how great it is, that it's almost AGI, the GPT-4o killer. Also here on Anthropic's website, the makers of Claude, you see these numbers here and different benchmarks and it all looks very impressive. But I wanted to know, is that true? Is that actually the case? To have a fair comparison, we're going to use the same prompts for Claude 3.5 and GPT-4o for both projects. Let's start with Claude. For this to work, you need to turn on artifacts. Funny enough, if you ask it to turn on artifacts for you, it tells you it doesn't know how to do that. When you ask it then where I can turn artifacts on, it also tells you it's not possible. So I'll tell you. Move your mouse here to the left, click on your email address and click on Feature Preview, and here you can turn artifacts on. The result is that when you prompt it, create a snake game in Python, you'll get the text on the left and the code on the right. Unfortunately, Claude is not able yet to run its own code, at least not for Python, so we still need to copy the code and paste it in our own Python script and run it locally. You can copy the code by clicking this button and then paste the code into your script and then run it. And here we see we have a snake game. And this is the point where a lot of YouTubers would say, oh look, how great, with just one prompt and everything's working. Problem is, though, you can do 180-degree turns. Yeah, and this shouldn't be possible in Snake. Even worse though, once you've eaten a little bit, and you change directions, you collide with yourself and you lose the game. This is a problem we need to fix. So we go back to Claude and tell it exactly that, and it will generate a new version of the code. Down here you can switch between the versions, so you can also go back in case it's missing something in a later version. However, even in version 2 of the game, 180s are still possible. If you're, for example, going right and hit down left quickly, it'll ignore the downturn and immediately go left and again do a 180 or hit itself. So again, we prompt Claude with this problem and it'll generate a new version of the code. However, in this version, if you hit down left quickly, it will simply ignore the second key input, so it will only go down, which is also not what we want. So again, in the same chat window, we tell Claude about this problem and it will give us a new version of the code. And in this version, the problem is fixed, so it will not ignore the second key input. Only problem is 180s are possible again. So in a way, we took a step back. At this point, you know the drill. We go back to Claude, tell it about the problem, we get a new version of the code, try that out. The problem in this version is that rapid key inputs are ignored. So if you hit down left, the left turn will be ignored. So one last time, we tell Claude about this problem, and this time it's actually fixed. Now, Snake is actually playable. We cannot do 180s, we can do rapid turns, we can hit keys in rapid succession and they will not be ignored, and we didn't have to touch a single line of code. This is pretty good, but it still took us 6 iterations to get to a playable game. Let's compare that now to GPT-4o. We prompt the same text that we used for Claude, create a snake game in Python. You get the text and the code in the same window, which is a little bit less convenient because you need to scroll more, but you can still just copy the code here, paste it in your Python script and run it. And when we do that, we get this game, which is also working on the first try. The game area is a little bit larger than before, but also here 180s are possible. So we get the same bug that we had in Claude, and we also use the same input to try to fix it. However, if you're going right and you hit down left, it just goes left, and a 180 is still possible. So we go back to ChatGPT and use exactly the same prompt that we used for Claude in order to try to fix it, and we get the same solution with the same bug that if you're going right and you hit down left quickly, it will simply ignore the second key input, so it will not go left. We tell GPT-4o about this problem. This version of the code doesn't even run. We get an attribute error. Copy paste that into ChatGPT, we get a new version, the error is gone, but the game window doesn't open. So for the 6th prompt, we tell GPT about that too. However, in this version again, if you hit down left quickly enough, then it will ignore the second key input. I tried to fix that in 2 more iterations, iterations 7 and 8, and this problem persisted, so this was not solvable. So in summary, Claude wins this comparison because we actually have a playable game after 6 iterations, and also these artifacts windows make it a little easier to switch between versions and to keep an overview after many prompts, whereas in ChatGPT you have everything in one window and just need to scroll and scroll and scroll to get to older versions, and you also don't have any numbering or something that would indicate which prompt number you're at this point. The version numbers that you saw I actually edited in post-production, and that makes it a win for Claude. Let's move on to the next example of the Electron particle cloud, and this time we're actually going to look at the results side by side with the same prompts of Claude and GPT-4o. So let's start with the first one. Create a 2D particle cloud in a circle in Python in a way that is animated. In GPT-4o, I additionally had to prompt it to please draw the circle in order to actually see the circle in the simulation. And we see the results here. In Claude, we simply have a rotation movement going on. And in GPT-4o, we just have random positions that are updated at every time step. Both not too useful, but a good start. So let's move on. Second prompt, now make those particles electrons that repel each other. In GPT-4o, this is pretty much what I wanted to see at this point, and we got there in just 2 prompts. Whereas in Claude, we have some damping term that I didn't ask for, and everyone who's ever been to a physics class knows that all these problems are usually solved in a frictionless vacuum. And this damping term is supposed to take care of these high velocities, but even though the damping term is there, you still see those high velocities in the simulation. Also, the boundary condition isn't exactly what I was hoping for, because here the electrons are reflected from the boundary. In a classic electron cloud simulation, the electrons should be pushed out to the boundary and then stay there. For the third prompt, we diverge a little bit, because for GPT-4o, we can already ask it to add a slider to control the simulation velocity, because all the physics is already working. Whereas in Claude, we need to tell it to remove the damping term and make the boundary non-bouncy. For GPT-4o, we pretty much get what we wanted, so we have a slider, we can control the simulation velocity, and the physics still seems to be intact. Whereas in Claude, we see that the electrons in the boundary can pass through one another, which shouldn't be happening due to the electrostatic repulsion force. So my guess is that the time step is too large. So for the fourth prompt, we ask Claude to fix that and also to add a slider to change the simulation velocity. Whereas for GPT-4o, we can move on to the next step, which is counting the particles that are inside of the circle and the ones that are on the boundary, and add a second graph that shows how the number of particles inside of the circle are slowly declining over time. However, when we ask GPT-4o that, we get an error message, so the simulation doesn't run anymore. When I copy-pasted that error message into GPT-4o, it changed something about the code, but that just gave me continuous errors that were produced in a loop. And when I pasted those in, it gave me even more errors. So at that point, I gave up for GPT-4o. So we have a version that was working, but we couldn't take the next step. So let's see how far we can get with Claude. After we asked it to make the time step smaller and to add a slider to control the simulation velocity, the slider that Claude added actually controls the time step of the simulation, which is a bit risky, because if you make the time step too large, the simulation will become unstable. So ideally, the speed slider should just control the animation speed, but not change anything about the math of the simulation. And despite me telling Claude already about the problem of electrons passing each other, it was still happening in this version. So I prompted Claude exactly that. However, Claude's solution attempt was to introduce a min distance parameter, basically saying that if 2 electrons get too close to one another, they're being reset, which shouldn't be necessary if the electrostatic repulsion is implemented properly and the time step is small enough. So I didn't even run that version, I just told it to get rid of this min distance parameter. However, when I ran the next version, I got a runtime warning in the console, and the particles moved extremely slowly even at maximum slider speed. With that version, Claude just made the slider control the time step again, which we already eliminated. So I asked it to just go back one version and fix the warning that we had, which again made the simulation extremely slow, so then I asked it to fix that. However, the last version here was so computationally heavy that it actually crashed my laptop. So this is the point where I gave up, and I tried one last thing. Take the code from version 4 of GPT-4o, paste it into Claude, and continue from there, and see if we can get this second graph working. And here in Claude, this worked, with the only problem being that the x-axis for our plot stops at 200 frames, so after a certain time, we don't see any updates anymore. So we asked Claude to adjust the plot so we can see everything until the electrons are all on the edge of the circle. The next version actually gave me a warning, and there was nothing to see on the graph. Copy-paste that in. And then we actually get a version that is working, where we see everything we want to see. However, also here, this slider controls the time step. And after a certain threshold, the simulation becomes unstable and electrons can pass through one another again. I played around with it a little bit. Around a time step of 0.15, the simulation becomes unstable. So rule of thumb is, once you have determined your maximum time step, just take a factor of 10 less than that, just to be on the safe side. So we ask it here to fix the time step to be 0.01. We finally have a version that does what we want it to do. So the time step is fixed at a value that is low enough to be stable, but with a slider we can control the speed of the animation. Having that, I try to do 2 more things just to test out the limits of Claude. Everything we've done so far uses the Eulerian time integration scheme, so where you basically have your force and you multiply that with your time step dt, which is the simplest way of a numerical time integration, but it's not very robust, it doesn't conserve energy, there are a lot of problems with the Eulerian scheme. I asked Claude to replace the Eulerian scheme with the Runge-Kutta 4 or RK4 scheme, and this actually worked on the first try, so the physics is still intact, the RK4 scheme is working. We probably can choose a higher time step now, because with the RK4 scheme, basically what it does is divide every time step into 4 sub-time steps, just to update the forces, because the particles have already moved a little bit, so the forces will be slightly different. When you're writing simulation codes like this one, especially when you parallelize it and then run it on supercomputers, one of the difficult things is to determine which maximum time step you can use. Because if you choose the time step, for example, to be 10 times smaller smaller than it needs to be, then the simulation takes 10 times more resources to run than it needs to. However, if you choose the time step to be too large, you get unphysical simulations like what we've seen before. Now, there are some analytical models with which you can predict the maximum time step. However, also those are a bit shaky because they don't take into account all the details of your simulation code. So most of the time what it boils down to is that you have to try it out yourself. Let's see if Claude can do that for us. And the text answer we get from Claude is actually quite good because it tells you in the theoretical considerations that because the repulsive force is proportional to 1 over r squared, this term can become quite large. So the closer the particles are to each other, the smaller the time step needs to be. And it also tells you that we could use an empirical approach. So to find the maximum stable time step, you could implement a binary search algorithm, and actually implements it here on the right. And here again is where I'm not too satisfied with the answer. In principle, the definition of the find max stable dt function is how you would do it. So you define some dt min where you know your system to be stable, you define a dt max where you know it's unstable, and then you basically do a binary search. So you always take the one in the middle. If that one's stable, you look for all the higher dt's, and if it's unstable, you look at all the lower dt's. So that part is good. However, the criterion for whether a simulation is stable or not doesn't make too much sense here, because all it does is check for nones in the x and y values and whether any of the x or y values are larger than 10 times the radius. Basically, whether particles are outside of our circle. And as you saw in any of the simulations, that never happened. By that criterion, all our simulations so far were stable, which they were not. But it also tells you that here, that the stability criterion is somewhat arbitrary. You might need to adjust it based on your specific requirements. Which is why for our very last prompt for Claude today, I asked it to add this criterion for electrons to pass each other in the boundary. Because when that happens, we know the time step is too large. However, if we look at the code, all it really did here is to check whether the angle of a particle on the boundary has changed more than 90 degrees in one time step. And that is correct as an instability criterion. If a particle moves that far, then we're definitely at a time step that is too large. But it might just move 10 degrees and pass another particle, and this check will not get that. On top of that, we were at a point again where Claude gave us a runtime error. So this is the point where I stopped this test. So in summary, I'm not entirely sure how to judge this because GPT-4o got all the first iterations right, but then got to a point where it just created errors. Whereas in Claude, we couldn't get it by itself to give me a physical simulation, but then once we prompted it with the proper code from ChatGPT, we could get all the later versions right. So in summary, I would call that a draw for the Electron Cloud simulation. Let's finish up the video with a quick test of GitHub Copilot in VS Code to see if we can reproduce the particle cloud simulation. First of all, the pricing of GitHub Copilot is around $10 a month, but you can get a month for free to try it out, and then you install the extension and you can use GitHub Copilot here inside of VS Code. To give Copilot a head start, I also copy-pasted version 4 of GPT-4o in here so that we have that as a starting condition. The first question I then asked Copilot is, can you read the entire code in the file that is open? Which gave me an error message. I asked, why did this happen? Gave me the same error message. How does this work? Give me the same error message. Explain the selected code, same error message. I googled the error message and turned out it was because of some mismatch between the version of GitHub Copilot that I installed and the VS Code version, so I had to reinstall VS Code in order to make that work. Just in case you have the same problem, this is how you fix it. Then I asked it, does it work now? And it gave me an explanation of the code, so it understood what we're trying to do here. Next, I prompted it the same thing that we prompted GPT-4o and Claude before, add a counter of the particles that are inside of the circle and to add a graph to see how they decline over time and to let us choose higher simulation speeds. That gave us a code snippet, but it assumes that all the other necessary initializations are already done, so now you would have to integrate it by hand into what you already have, which is not what we want to do here because we ideally don't want to touch any line of code whatsoever and try to make it work. And on top of that, and this part seems a little dumb, it suggested that to allow even higher speeds, you could introduce another slider or parameter that multiplies Vx and Vy by a factor greater than 1, increasing the particle speeds. Basically not using our slider to increase the simulation speed, but just have another slider to increase the speed of the particles, which is obviously not what we want. But it also doesn't have all the context that Claude and GPT-4o had, so we can forgive that maybe. So next I asked it, can you create a new file and add the code that you suggested to it? And it answered, sorry, I can't assist with that. So next I asked it to give me the code it gave me before as a complete operational script with all the initializations in it, and take whatever it needs from the code that we gave it, so the version 4 of GPT-4o. Then it gave us this script, and I copy-pasted that into a new file and ran it. However, it deleted the slider, and also the circle isn't drawn anymore. So it deleted parts of the simulation that we already had and that we wanted to keep. Next, instead of using this chat window on the left, which is basically just ChatGPT again, just integrated into VS Code, we use the inline AI feature, which you can see here with these 2 stars. When you click on it, you can ask Copilot a question or type something for commands. You can also open that with hitting Command I on Mac or Control I on Windows. Here I then prompted it the same thing, so to add a counter, add the second graph, and to let us choose even higher slider speeds. And as a response to that, Copilot deleted all our import statements and also a bunch of other stuff in the code, so that the script didn't run anymore. Unfortunately, I didn't record that part when I did it, so you have to trust me on that. So in the next iteration, I prefaced the prompt with leaving the code intact. Can you add the counter, add the second graph, and let us choose higher simulation speeds, which added the code at the beginning of the script in front of the import statement, so exactly where I prompted it. It didn't automatically add the code where it needed to be added. So then I asked it, can you put the code in the right place in the script? And it answered, no results, please refine your input and try again. So for the 6th iteration, I figured maybe we need to make sure it understands the script first before we ask it questions to improve something about it. So I asked it, can you read and understand the entire code in this script? And it answered certainly, and put some placeholder code in there that I didn't ask for. So 7th iteration, I tried again. I said, explain what the code in the script does. Then it actually gave me some decent explanation of what the code does. Unfortunately, I cannot show it to you here because the window that it shows these answers in is relatively small. So now that it understood the code, I figured now we can ask it again, add the counter, add the second graph, let us choose higher velocities on the slider. And it said it made some changes, but it just added some code at the end of the script so that we had 2 plt.shows, for example. So it didn't integrate the new code that it generated with the code that was already there. So then I asked it, now we have 2 plt.show and potentially other problems in the script. Can you fully integrate your changes to the rest of the code? And again, we get the charming answer of no results. Please refine your input and try again. So after 9 iterations with GitHub Copilot and not a single useful output from it, I felt like taking my laptop and throwing it against the wall. Luckily, I didn't do that. Instead, I figured we can give it one more chance. We can start from 0, delete all the code, and let it come up with its own code. Maybe then it's better, right? I started over with our very first prompt, created 2D particle cloud in Python in a way that is animated, which gave us this still image and this error message. So also here, not great. Because it's GitHub Copilot and it can in principle read the code, it can read the terminal output, I figured it can fix its own errors. But apparently it can't, because in the next iteration when I asked it to add electrons to the simulation, it just added code at the end, but didn't change anything about the code that was already there. So we get the same error message. In the next prompt, I needed to copy paste in that error message, asked it to fix it. In the end, it just had to make one variable global in order to fix the error, so it wasn't something massive, but still, why does this happen in an AI that is supposedly so intelligent? But at least now we get the simulation here where the particles are moving counterclockwise on an ellipse, not really a circle, but at this point I take it. So for the last iteration, I asked it to put the particles in the middle of the circle without any initial velocities. So we get more or less the same picture that we had before. It changed something about the code, but all it did is actually give us a circle this time, but all the particles were still initialized on the boundary. And at that point, I gave up. I kept the last part about GitHub Copilot intentionally short because in the next video, we're going to have a deeper dive into GitHub Copilot and how to use it the right way. But for today, it seems we get worse output from GitHub Copilot than we do from GPT-4o, which is surprising given that I am paying for GPT-4o, I am paying for GitHub Copilot. GPT-4o is what Copilot should be using in the backend, but we're going to see in the next video why we sometimes get output that is worse from Copilot than from ChatGPT itself. In summary, Claude definitely won the snake game comparison. In the Electron cloud simulation, it was a draw between Claude and GPT-4o, and GitHub Copilot goes out of today's comparison with 0 points. Before running this comparison, I actually expected Copilot to do better than the other two because it has the massive advantage that it runs on your computer and can read all the context of your code, and it also has the convenience advantage that you don't have to switch back and forth between a website and your code all the time, but it's just inside of your editor. It has the potential to be better, but it's just not, at least not for what we were trying to do today.